As always, we start with a brief recap, this time on differential kinematics and controls. We have been deriving the equations for the forward kinematics of a differential wheel robot in the past, and we have shown that you can also express this in differential form, where you relate the wheel speeds of the robot platform to the speeds in Cartesian space. This is indicated with a dot here, so this reads x dot, which is the time derivative of the position. You can also put the dot directly here, which is done there. And we argued that there is a general form where a matrix, which we call the Jacobian matrix, relates the velocities in the n-effector space to the velocities in Cartesian space. This Jacobian matrix consists of the partial derivatives of the positions in Cartesian space to the positions in n-effector space. So here the n-effector space are joint angles, and so we take the derivative with respect to of x, y, and z with respect to the first, the second, and so on joint. If you do this here, you would take the derivative of x with respect to phi left, and then the derivative of x with respect to phi right, and you will get a 2 by 2 matrix. And when you do this, you will find that you get exactly the equation that we have here. Why is this important? Because I argued that you can actually optimize a robot desired position in Cartesian space using a gradient descent approach, and we derived this by looking at a normal one-dimensional equation and looked at numerical ways to find the minimum, which is here for this parabola. And the idea was I pick some random point somewhere, and then I use the gradient of this function to drive toward the minimum. For this, I came up with this expression here, where my next guess for my optimum is given by my previous guess minus the derivative at that position of the previous guess times what we call a learning rate or a gain. And if you work this out using a learning rate of 0.4, you get something like this here. So I start at minus 0.2, and then in 5 steps I arrive very close to the minimum where the derivative is 0. When you plot something like this, you will see time evolution like the one shown here, where you make quickly progress and then slowly but steadily converge to the optimum. And this is the exact same behavior that we have seen when we programmed a controller that drives the robot to a desired position or turns it into a desired orientation. We have then also looked at increasing that gain, increasing the learning rate, and what we have seen is that when you do that too much, the system starts overshooting. So here we are overshooting over the desired optimum and then have to go backwards, and you get something that looks like this. And as you keep doing this, you will eventually get marginally stable oscillating behavior and eventually unstable behavior. So how this really works is subject to a field called control theory. You can take classes on this, usually in mechanical engineering or electrical engineering. For this, I just want you to know what the behavior is that you can expect when you play with these gains, and also give you some guidance on tune those behaviors. Now, we then show that the gradient that we've been talking about is really given by this Jacobian, and in a very general form, you can find out how you have to change the n-effector or the joint angles of a robot given a certain error by using the inverse of the Jacobian. And if you work this out for the Jacobian of the differential wheel robot, you indeed get an expression that gets you the wheel speeds that you have to set based on the error rho and alpha, which we have been deriving previously. Now, why is this all interesting? Well, we have a problem with feedback control. And the first problem is, and we've seen this very early on in this specialization, different behaviors cancel each other out. And so in the beginning, we showed you or you actually played with this yourself, when you have a light following behavior like shown here and obstacle avoidance behavior like shown here, you will end up with scenarios where both wheel speeds cancel each other and the robot simply stops. Now in this case, the same is true if you have a waypoint following algorithm where you don't use light and light sensors but GPS and positions, and you compute the wheel speeds using that controller that we just derived, and you have another controller that wants something else, you might end up with a situation that the robot cannot recover from. So the solution for this is to plan, pick a different waypoint, and then end up at the desired waypoint. You also have another problem. The resulting routes are not necessarily the shortest. If you don't plan, you don't know what's going to happen, how a route's going to look like. In this case, both of these routes are equivalent, but unless you actually look at the map beforehand and plan it out, you wouldn't know. And finally, a related problem, the time of arrival is unknown. So when you use Google Maps and you put in a request to go somewhere, it will tell you when you will arrive, and it will actually even probably select the route that gets you there the fastest. So how to solve this? We actually need to generate the waypoints from our configuration space representation. So in the past, we've been developing the concept of the configuration space instead of a basic map in which we can simply abstract the robot as a point. And in this case, I show you the three-dimensional configuration space for a non-circular robot that changes as a function of the orientation. And the question is, how can we get these waypoints that you see here to the right from a representation like that? So the answer is, you want to have a multi-layer architecture. At the very bottom, you want to have the feedback controllers that we've been developing once you have these waypoints. But then at higher levels, you want to actually plan on some kind of graph representation. And at the highest level, this is the Google Street Maps. This might be a building map for a robot inside a building. At a lower level, you might consider intersections and things like this, where you retrieve a little maps or graphs that encode how you, for example, do a left turn. And then at some point, you want to sample the environment and generate a graph on the fly that helps you to consider different trajectories, for example, to avoid these obstacles here. So the mathematical structure of choice for this is the graph. A graph is a collection of nodes and edges. In a street map, the nodes are typically the intersections and the edges are the streets. We are using directed graphs where the direction of an edge matters. So in this case, you can only go from A to B, but you cannot go from B to A. If you can do both, we have two edges, one that goes one way and one that goes the other way. And for simplicity, we usually just show two arrows. Now in the data structure, this is not the case, but I do have two edges. And what I suggest you doing is using a dictionary in Python as one of the simplest ways to encode a graph. And here I have all the nodes as the keys in my dictionary, and I have the edges encoded by nodes that I can get to from a certain node as a list. In this case, I can reach node B and C from A. I can only reach node D from B. And from D, I also can only reach node B. But you see here, I actually have encoded two edges in this graph, even though there's only a single line. This also leads to the concept of a path. In this case, a path from A to D can be a collection of nodes. So I have a list of nodes A, B, and D. And usually this is the desired outcome, a path like that a robot can follow. The dual of the directed graph is a graph in which all the edges are the nodes and the nodes are edges. And in this case, I came up with an equivalent structure. Here, the nodes are indicated by the edge names AC or CA, and I have a list of edges that I can get to. So these are not edges anymore, but they are nodes in the dual graph. And so you see I can generate one representation from the other. The reason I show this here is because the dual graph has a little more intuitive interpretation for the path, which is now a list of actual edges. So in order to get from A to D, I have to first use edge AB, and then I have to use edge BD. So now we want to think about the shortest path problem, and for that I invite you to briefly think about what the shortest paths from A to F, F to D, and A to E on this graph here are. Clearly from A to F, the shortest path is ACF. From F to D, I have to go F, E, B, D, and from A to E, I have to go from A via B to E. Now, why am I doing this? Well, I want you to think about a little more complicated version when I introduce weights, and now you see the problem is less trivial. When I want to go from A to F, I have to actually count the edge weights, and I end up with a cost of 8. And at this point, I have no idea whether there's a better path or not. So I have to try other paths, and in this case I can also go via B, and I end up with 6 plus 1 is 7, and therefore I get a cheaper route. Now I only know when I found the cheapest path after I've been exploring the entire graph. So I want you to think about the idea that you have to actually do this exploration. I also want to introduce the idea of completeness, which is when do I know that I have been exploring everything and found the optimal solution. Finally, the notion of cost has been arbitrary. We have just assumed that there is a cost of hops and that doing 2 hops is better than doing 3 hops. Later we introduced the idea of cost. Now hops becomes secondary. But in fact, the cost can be anything. It can be a combination of distance and the number of hops. It can be a combination of time and the number of turns. It could be a combination of energy and energy consumed or time. And this really depends on your application. And at the end of the day, you can reduce it to a shortest path problem with numbers such as these, which are associated with each edge. Now, to explore the graph, we have 2 options. One is called breadth first search and the other one is depth first search. In breadth first search, I go to a certain node, I look at its neighbors, and I explore both of these neighbors before I go deeper into the graph. So before I go from B to D, I will actually make sure I also explore C, and only then I go back to B and explore D, and then E, and then finally F. That is a very slow way of doing things, but what you end up doing is you can be sure that once you arrive at a certain target node, you have found the shortest path. Sometimes depth first search can be faster. In this case, I go deeper and deeper and deeper until I hit a roadblock, and then I go back. In this case, I went from A to B to D. I can't go any further. There's no connection between D and E, so I have to go back to B and go to E from there. I go deeper again, end up at F. This is the end of the graph, so I go back to the unexplored nodes. I see that node C is still unexplored, and I will then go to C. So the important thing here is that there are 2 central data structures that you use for implementing either of these. One is a first in, first out queue where you store your nodes. The other one is a last in, first out queue. And they look like this. The last in, first out queue is also known as a stack. The first in, first out queue is usually known as a queue. And there's one way to remember this. The queue is broad, so you do use it for breadth first search. And the stack is deep, so you use it for depth first search. So here's a simple algorithm, a simple implementation of breadth first search, and I invite you to go to a dedicated video on this where we show how this is done. I have my graph structure that represents the graph to the left. So you see here there is no node that I can go once I'm at D. There's no node that I can go once I'm at F. So these are all directed edges that are pointing down. And what I need is I need a set of visited nodes, which is initially empty, and I need a queue of nodes that I want to start. And in this case, I start with the node A. Now the idea is that as long as the queue is not empty, I take the first node from the left. So I use the pop 0 to actually take them in from the left, which is the first in, first out queue. And then I check if this node N is not being visited so far. And if that is the case, I add it to my visited list, and then I go through all of its neighbors. So in this case, I will draw the node A. I will then see that it's not visited yet. I will get the neighbors B and C, which I get here, and then I append both of those to the queue. So if I do this, I will explore the entire graph. I visit all the nodes in this order here, A, B, C, D, E, F. You can see this when you follow the live coding example. And now the question is, what do I have to do to change this to depth first search? And if you paid attention, the only difference is really the data structure. So all I need to do is I have to change it from a first in, first out queue to a last in, first out queue, or a stack. And so when I use the command pop, I will actually pop the last entry that has been appended. And in this case, I will get this order here. Now the question is, how do I find the shortest path, which is something that I'm interested in. I keep using the algorithm that I just developed. In this case, I keep using the depth first search algorithm. And what I do is I add two more data structures. The first one is I keep track of all the distances from the any node to the start node, in this case A. And so I set this initially to 0. All the other ones are set to infinity. And I create a data structure that keeps track of the previous nodes. So in this case, it's a dictionary where every key is a node, and I can store the node that I used to go there using the shortest distance. So I use the same exploration algorithm. It doesn't matter whether it's BFS or DFS, but what I now do is I keep track of the distances, and I compute the new distance by taking the old distance to this node, and I add 1, because every time I go deeper, I increase the distance by 1 hop. Now, if the new distance is smaller than the previous distance, and remember I set them all to infinity in the beginning, then I will actually store this new distance to the node, and I update the previous node of that node. Now, in the case of the node A, the distance has been 0, so I will actually find out that the new distance is smaller than infinity. I therefore set the distance to be 1, and I store that I have gone to B via A. So with that, I have a data structure that allows me to find the shortest path from any node here to the start node A. Now, this doesn't really work once you have edge costs that are non-uniform. In this case, I added edges like 3 and 5. And so you already see when I do breadth first search, there isn't really a point to further explore node C, which has been very costly to go to, because it's a lot cheaper to stay on this route here. And indeed, when I get to D, I'm still 1 cost below this cost here. So it makes sense to always explore the node which has the lowest cost to my starting location. And the data structure to do that is known as a heap. In the heap data structure, on top is always the node with the lowest cost. In Python, I can do this by heapifying the queue, but I also have to introduce the cost. So instead of just storing the nodes in the queue, I store a tuple, which is the node and the cost to the goal. I do this in this order here because this is how the Heapify library in Python works. It will look at the first entry of the tuple to sort the list, and so this item will always be first because it has the lowest cost, and when I pop it, I will get the one with the lowest cost. But then when I put the new ones onto the heap, which I do here using the heap push function, I actually push the new node as well as the distance to it as a tuple onto my heap. So this way I will always explore the node with the lowest cost to the goal first. So again, you only need this once you have non-uniform edge costs, which already happens when you start introducing diagonals in a grid. Now you might wonder, how do I turn a graph like this into a grid? In this case, I have the graph here, and what I can actually do is I can exchange all the labels that have been characters so far to tuples. Now you can see if I have a map like this, I can index all of the nodes of the map with tuples. So this is the tuple 0, 0, this is the tuple 2, 2, and I could create a graph structure like this one using tuples. Here I have simply replaced the node B with a tuple 3, 2, which is an index to a map, which is not shown here, but I just want to get you the idea across that the Python dictionary doesn't care about whether I use strings or tuples as an index, and so I could ask what are the neighbors of tuple 3, 2, and I will get a list of characters, or I could ask what is the neighbors list of the node A, and I would get a tuple in return. So you can now see that I can create a graph structure like this using tuples, and I can take a map like that and turn it into a graph. Now, in order to do this on the fly, I can also come up with a function called getNeighbors, which returns a list of tuples as for every tuple on this map. And in order to do this, I come up with this data structure delta, which keeps track of all the possible motions. In this case, the robot can only move right or left and up and down. I can then compute a candidate tuple using this by looping through this delta data structure. I then check whether this candidate is within the bounds of my map, and if it is, I can check whether this candidate is actually navigable or not. In this case, the map uses ones to indicate obstacles, so a path will need to go around this. And then if that is the case, I add the new candidate to the neighbor structure. So with this, I can simply replace the lookup, where I look up my graph dictionary with this getNeighbors function, and all of the algorithms work as before. Now, Dijkstra's algorithm has a big drawback. It actually expands a wavefront in any direction, and so you will go in a lot of direction that you already know you will never get to the goal. And a solution for this is the A* algorithm, which actually uses a heuristic to expand toward the goal. And what you see here is the Dijkstra has been expanding directly toward the goal until it hits the obstacle. Then it does wavefront expansion like Dijkstra's, and as soon as it finds a shorter way to go to the goal, like now, it will actually shoot there directly. So how is this done? I use the same algorithm as before. I use a Dijkstra's algorithm where I draw the node with the shortest cost to the goal, but this time I encode not only the cost that I have been already incurring, but I'm also adding an estimate of the cost to the goal at every point. This is known as a heuristic, and in this case I add the Manhattan distance. So you see here goal x and current x, and goal y and current y, and so I at the Manhattan distance at every point to the goal. And now if I explore around the start, the Manhattan distance to the goal to the right is lower than the one to the left, so the algorithm will choose this node first to explore. I have also graphically done this here on a simple grid. Now the first number is always the hop distance to the start. So you see this is a wavefront that goes circularly around, but the second distance is the Euclidean distance to the goal, or in this case the Manhattan distance. So you can see the cell to the right has a Manhattan distance of 15, the cell to the left has a Manhattan distance of 17, together 16 is less than 18, and so the algorithm will keep going, exploring in this direction first. Now as soon as you hit the obstacle, the other things become equally attractive, the other nodes, and the algorithm decides to go this way and finally finds a shortest path to the goal, going around the obstacle around that direction, and doesn't have to explore all of these other nodes that Dijkstra would possibly have explored. So in practice, A star is the algorithm you will use to plan the shortest path across graphs in robotics. I want to give you a couple of tools to visualize things better. You can actually visualize a grid map like you created in VBots using the matplotlib library and use emshow for the map. I turn on interactive mode like this. So what I can do is I can, whenever I compute a new cell, I can show it and then I pause a little bit so that the map actually updates. And here I plotted the goal using a star in yellow. The other ones are green and red, so you can guess the characters for those. And I'm using the dot to print these points. Here I have the visited nodes in yellow and the open nodes in green, and at some point all of them get visited. When I hit an obstacle, it goes back to the previous ones to look at them again, because they are now becoming attractive with the heuristic. And once the shortest path is found, or any path is found, I mark them all as red. So in summary, we need planning to get the shortest path to a goal. We need planning to get deadlock-free paths. So as soon as we are stuck, we want to explore different locations to create better routes to get there. And finally, we want to use planning to predict the behavior of the robot. No matter what the cost function you choose is, you can always reduce this to a shortest path on a graph. And here you probably want to use the A star algorithm, which is a priority heap with a heuristic. This is usually the simplest and best way to do that. Edge costs can be anything, not just distance, but time, energy, or even the number of turns or the accelerations that you need to use so you can get a smooth ride. And with that, I will let you implement this in VBots.